Okay, so welcome everyone, and thanks for joining this webinar dedicated to BERT's classification for everyone in KNIME. So let's just briefly go through housekeeping. So in case you have any questions, I would be glad to answer them. So please leave your questions in a Q&A tab in your web application that you use for watching this webinar. And yeah, I believe it's time to start. So first of all, let me introduce myself. My name is Artem Ryasik. I work in Redfield as a data scientist. Redfield is an elite partner of KNIME, and we work in areas such as data engineering, data science, network analysis, text mining, anonymization technologies, database administrations, cloud solutions, and so on. And also, we are developing KNIME extensions. So for now, we have already developed and released 5 extensions, and one of them, BERT Extension, I'm going to present today. So this is a short agenda for today's session. So I will briefly explain the BERT. I will avoid any math or some complicated stuff. I will just keep it quite abstract. Then I will present and just explain the BERT nodes for KNIME. Then I will tell a little bit more about today's live demo and the data set and the task that we're going to solve. I will talk about a little bit about the parameters, then we'll follow the live demo, and finally I will just briefly mention about our future developments regarding this BERT extension. So BERT was released in 2018 by Google, and that time when it was released, it became state-of-the-art model that regarding the NLP, natural language processing tasks. So as you can see on the top picture, it did so well on Squads 1.1 dataset. It even did much better than human performance. It also did very well on other datasets and use cases and the tasks related to them, such as COLA, SST2, and some others. So these are just the names of the publicly available data sets. And here you can see the scores for BERT and some other models. And for this year, there is just a short update for 2020. They're showing the 5 models that are now state-of-the-art. And as you can see, there are 3 representatives from BERT family. So Albert, Roberta, and BERT, all of them are coming from, they are like ancestors of BERT. So as far as I remember, Roberta is a model that was trained by Facebook. So now let's talk about some concepts of BERT. Why it's so powerful and how it was trained. So the main concept of BERT is transfer learning. So transfer learning can be applied to many models, not only BERT, let's say image recognition as well. So, and it contains of 2 steps. So the first step is that we build a neural network, an architecture of neural network. Then we take some data, some specified data, we prepare it, and then we train the neural network from scratch. We assess and estimate the model. If we are satisfied, we can say that, okay, this model is good, it's robust, and so on. And then we can use this model to, let's say, fine-tune it for our more specified tasks. So fine-tuning usually means that we take the model and add some additional layers to this model, maybe just 2, 3, 4 layers. We basically expand the neural network a little bit, and then we take a specific data set for our task which is much smaller than the data set that was used during the pre-training, and train this combined model. And after that, we get quite good results. So this is exactly what Google did. So they took a just enormously big data set that included Wikipedia, articles, and books. So they have built extremely deep neural network, trained it, and released it, and they gave it to community. And how can casual user might use BERT? So basically here, let's say we would like to train a simple binary classifier that distinguishes the email, whether it's spam or not spam. So basically we build on top of BERT, very simple, very shallow network. And then we provide a special data set regarding to this task. So we train this model on the corpus of spam and not spam emails, which is quite smaller, maybe just several thousand emails. And that's it. We use this model. So how BERT was trained? So that was the whole concept of BERT, of transfer learning. So the BERT was trained on two main tasks. The first one is prediction of missing or masked words. So we have the example. So the man went to he bought of milk. And even for a human, it's quite obvious and obvious task. So then we can quite easily match some words that perfectly fit these sentences. And another task that was used for training BERT is next sentence prediction. So this allows the neural network to understand the semantic and the logic of notation of the texts. So here we have two straightforward examples. The man went to the store, he bought a gallon of milk. So yes, for us, it's quite obvious. These two sentences might occur one after another. But the second example doesn't make any sense. So the man went to the store, penguins are flightless. So it's very unlikely that these two sentences might occur in one text, or at least one after another. Some more stuff. So BERT has quite sophisticated architecture, and it uses two concepts, transformers and attention. So basically, transformers are hidden in the name of BERT. It's bidirectional encoder representations from transformers. Transformer is a special type of a neural network, of a layer of a neural network that contains of two parts, encoder and decoder. Right now, we are only focused on encoder. Encoder basically encodes or translates natural language to BERT language or to machine language. Basically, it creates the vector representation called embedding for every word. And every word, even if it's the same word, might have its own vector representation because it's based on the context of this word. So that's why it has this bidirectional word in the name. So it considers the context before and after specific word. Another type of layer that is also used in BERT, it's called attention. This mechanism allows to understand which words are important in some specific context and which are not. So let's take a look on these two simple examples. You can see them on the slide. So the animal didn't cross the street because it was too tired. And the second one, the animal didn't cross the street because it was too wide. So for a human, it's quite obvious to which word it refers to animal or to street. So, this attention to the context is extremely important in such tasks as next word prediction or next sentence prediction, or in tasks such as translation from one language to another. So in English, in this case, it's quite straightforward. So animal and street, these words both have neuter gender, but in other languages, let's say Spanish, French, German, these words might refer to these words might have different gender, and in order to perfectly match the noun and pronoun, we need to have this attention. And another thing is that BERT was trained on more than 100 languages, so it also perfectly fits for tasks not only for English, but other languages, and also it fits really, really well for translation from one language to another. So that were the basic concepts of the BERT. Now let's talk a bit more about the extension. So obviously the BERT is quite a huge topic, and it has a big amount of applications. So we started from one of the most frequent and most common NLP task, text classification. So we have implemented this step first. So this extension was released about a month ago. It's available, so you can just download it right now. And currently it contains 3 nodes. So the first one is model selector. This node allows you to get a model from TensorFlow Hub and cache it on your disk. So after that, once you have this BERT model, you can feed it to classification learner. Then you need to provide training data, and that's it. So it will automatically add a simple classification neural network on top of BERT model, and you can train it. Once your model is trained, you just feed it to predictor, and you can apply your model or deploy your model. So basically, we were trying to follow the same strategy, the same scenario as KNIME has with learner predictor node. So you partition the data, you learn the model, you test the model. Let's take a look on the settings of some of the nodes. So the first one, BERT model selector. So you can download the model from TensorFlow Hub. So currently there are, let's say, 8 canonical models provided by Google. And here is the list of these models, and you can download them. So let's go through the notation. So EN stands for English, multi stands for multilingual, and ZH stands for simplified Chinese. So cased and uncased. Cased means that the case of the tokens of the words in the text will be considered. Uncased means that everything will be considered as lowercase letters, lowercase words. And also these parameters, L, H, and A, stands for the size or the number of different blocks in the neural network. So today we are going to take these 2 models because they have the same type of parameters, and as long as we are going to use 2 languages, English and Portuguese, we can consider these models to be quite equal, so we can compare the results provided by these models. So the data set and the use case. Today we are going to have a live demo dedicated to text classification. And we took a data set that is called DBpedia classes. So it provides, it's a very nice and huge data set, but unfortunately it only has English texts. So we managed to enrich ourselves this text. We just took the dump of DBpedia, and then we merged it and joined it by the names of the Wikipedia articles. And then we got the data sets of the equal size, about 33,000 excerpts for every language. So how does this data set look like? It's quite simple. You can see some snippet of this data set on the screen. So it contains Wikipedia name of the article in English. Then goes the text. It's not the full text of the article. It's just abstract. So usually it's quite short. And then there goes 3 hierarchical layers of labels. So the first one is quite common and shallow. The second one is a bit broader, and the third one is even broader. So you can see, so like let's say level 1, it's place. Then we can like go what kind of place, infrastructure, then what kind of infrastructure, airport, and so on. And yeah, you can see for every level we have different number of classes. So level 1 is 9, level 2 71, level 3 219. In our demo, we are only going to work with level 1 and level 2 because level 3 is it's too broad, and usually the data set for every class becomes extremely unbalanced, and there are just several representatives for some rare classes. Yeah, training parameters. I will show them during the live demo. So yeah, BERT classification learner. So once you have got your data and you got your model, I mean the BERT model, you can go to the next step, classification learner, and these are the settings of this node. So at the first tab called settings, the only thing you have to do is just to set up the sentence column, the column with the text, class column, the column with labels, and provide the maximum sequence length. Maximum sequence length parameter is responsible for how many tokens or words starting from the beginning of the text will be considered by BERT. Currently, BERT has limitation of 512 tokens. On the second tab called Advanced, you can provide training settings. So the first parameter is number of epochs, basically how many times you would like to train your neural networks on your training data set. And the batch size. The batch size defines the portion of data that is used for updating the weights in the neural network. Another parameter is called fine-tune BERT. So if it's active, then BERT weights will become trainable. If it's not active, then you will only train the classifier built on top of BERT. So obviously, if you activate this checkbox, it will significantly increase the training time. However, usually it's worth doing fine-tuning BERT as well. It will provide better results. And finally, you can pick the optimizer and provide its parameters. So this is the workflow that we are going to look at today. It's already available on KNIME Hub, so you can download it just now if you're extremely curious. And I really encourage you to take a look at this workflow, maybe not now, but after the presentation. So its name is DBpedia Text Classification with BERT by Redfield. Also, you can get it by this link. The slides will be available after the presentation. All right, so now let's switch to the demo. Let's just briefly go through. So as you can see, I have everything executed because training might take, quite a lot of time. So the first node here, basically is components. I just included some, let's say, general or global parameters here. So the number of epochs, I set up to 3. Batch size, I set up to 28. You have to set up this parameter with care because you need to think about what kind of hardware you are using. So if you're using GPU or CPU, of course it's advisable to use GPU, but yeah, you need to consider your RAM or video memory. So max sequence length, I decided to set to 128. A bit later, I will explain why. And here we have a switcher between the texts, so English and Portuguese. It automatically, if you pick English, it means that you will automatically read a proper file for English and a proper model for English. So as you can see, all these settings here, they are overwritten. So you don't have to bother about this. So the model and the text are synchronized. Then goes a text assessment component. It's quite handy. It gives you some understanding, some statistics about the length of the text. So the mean length of the text is about 130 words. The median value is 96. So maximum and minimum just gives some understanding about the range. So as long as the mean length of the texts equal to 130, so that's why I picked this max sequence length equal to 128. Then you can see two branches called L1, L2. Basically, these branches are dedicated to learning with labels from class L1 and labels from class L2. So here I also have a component that allows you to count the occurrences of every class. So it has a dialog, and the output looks like this. So it basically gives you the information about how many class representatives we have in our data set. And as you can see, we have extremely rare classes here. It's just, obviously, it's too unbalanced. So that's why I have added a filter. And the filter dialog is very, very simple. You just set up the threshold for minority class. So it will filter out all the representatives of classes if they occur less than 100 times in the data set. So basically, if we had 9 classes, afterwards we will have 6 classes. And also it automatically splits the data sets into 3 sub-data sets. The training data set, validation data set, and test data set. So in BERT classification learner, you don't have to provide any parameters. Probably, if you are willing to, you can pick different optimizer or provide different parameters, because all other settings are, most of them are overwritten by this component in the beginning. All right, so we have trained the model, then we apply the model, and then it's time to assess the results. So as you can see, this triangle, it's the same as if you were using a partitioning node, random forest learner, and random forest predictor. So then we just use this domain calculator to update the table spec. So KNIME is quite sensitive to the quite broad range for categorical values, so we need to just recalculate them. And also I use timer info just to get the information about the execution time. And finally, I prepared the dashboard. It's quite complex, so let's take a look at this dashboard. So here, on the left-hand side, we have a stacked area chart that shows the percentage of class shown by blue color, and the percentage of misclassified shown. So everything are the percents. So we can see that place class was mostly misclassified. Then on the right, we have a plot for the loss as the function of epochs. And here, basically, we can. I have trained it for 3 epochs, and we can see that validation loss started growing. So basically, we could stop training after the second epoch. Then goes average model statistics. As you can see, we got incredibly good model with the accuracy 99%, F1 99%, coin kappa 99%. It's just almost perfect model. And at the same time, it seems to be not really overfitted, which is also good. Then goes information about the execution time. So as you can see, it took 30 minutes on my computer to train for 3 epochs. So roughly 10 minutes per epoch, and less than a minute to predict several thousand records with a trained model. Then on the bottom of the slide, you can see some kind of a confusion matrix. So it's probably not really okay. Yeah, let's take a look. Sorry. Then I build a table for misclassification analysis. So what we have here. So first of all, I provide the absolute number of texts for every class. So we can see that this data set is quite unbalanced. Then we have text in relative numbers, basically the percents. Then we have the misclassification count. So basically, in total, we have just 16 misclassification for more than, I guess, 4,000 texts, which is really, really good. Then goes misclassification counts, but percentage. It's percentage over all misclassifications out of 16. So, yeah. And finally, also we have here misclassified mode, which shows what was the most frequently misclassified. So usually agent was misclassified with place, or most frequently event was misclassified with work. And then goes the error rate per class. As you can see, it's almost zero for every class. Well, it's kind of obvious because we have 99% accuracy model. And finally, there goes the, I call it dynamic confusion matrix. It's a little bit disorganized, as you can see, but I will explain why. So for the current use case, when we have just 6 labels, we can fit everything into one screen. So here we can see which classes were misclassified with which other classes. Probably it's not that interesting to look at this table for L1 classes. So let's refer to L2 classes. So the idea here was completely the same. I trained on the same text, but different labels. And now we have, it's less than 71 class, but still, I guess, more than 50. Let's take a look on this model. So again, these plots will give us the information about the most misclassified classes. So right now it's person, the second one is sports manager, and the third one is athlete. So this model also could be stopped training on the second, after second iteration. So now we have slightly lower accuracy and slightly lower different parameters such as F1 and coins kappa. Training time, it took the same time both for learning and predicting. So here, now we can see much more classes. Let's just see which class was mostly misclassified was person, sports manager, politician. So now, let's refer to this dynamic confusion matrix. So this component has a dialog. This is kind of a zoom on the confusion matrix. So as long as we have so many classes, here is the list of these classes. It's quite big. If I would put the whole confusion matrix, it will be unreadable. It will be really hard to read. So instead, I made this confusion matrix a little bit more dynamic. So user may pick some specific classes in order to see how well the prediction was for these specific classes. So I tried to pick the classes that kind of similar to each other and might be misclassified. So sports manager and athlete, and the second pair is artist and actor. So let's see. Let's see. So basically, actor was never misclassified with the artist. Instead, it was 3 times misclassified with person. And the same for artist. It has never been misclassified with actor. Instead, it was just 1 time misclassified with athlete. However, the story is quite different for athlete and sports manager. It seems that these classes are very, very similar to each other. And as you can see, we have quite big amount of misclassification. So sports manager was misclassified with athlete and vice versa. However, athlete seems to be more straightforward for the model rather than sports manager. So you have this kind of workflow on the KNIME Hub, but I also, just in case, put some copy of this workflow, but instead I used Portuguese. So we can just briefly go through Portuguese models. So the first one, L1 labels. So here we have slightly different statistics and the learning rates. It was always increasing, so probably we could try to have one more epoch to train. But anyway, this model is also very good. Training time was the same, so misclassification. Yeah, so unfortunately I don't remember exactly, but probably it's worth comparing the misclassification. But for level 2, for L2 labels, I also picked the same sports manager, athlete, and artist actor. So I found some a little bit surprising results. So the model is a bit worse. For L2, for English, we had about 97%. Now we have about 95%. But what I found is that for Portuguese language, it seems that sports manager, so yeah, we have a little bit more misclassification between athlete and sports manager. So I don't know whether it's a quality of the texts or maybe it's a specific of Portuguese language. Who knows? But we can see that some results, they are different. They're so different. They are drifting. So that was a short demo. And yeah, let's get back to the slides. I just have only a couple of them. So future development, obviously there are a lot of work need to be done in order to increase the range of use cases for BERT, and a lot of stuff needs to be done to make it very comfortable to use in KNIME. So currently our big goal is to expand the number of models that are compatible with our nodes. So we are working both on Google TensorFlow Hub and Hugging Face models to be supported. So it will increase the range of the models. This is especially important in case somebody would like to pick some specific model that was trained on specific language, because there are already quite a lot of models that are available for specific models. So I definitely know that there are French birds called Camembert, Swedish birds called Swebert, there's a Russian bird called Rubert, and definitely there are some other models. Another improvement for classification, as we see, is a multi-label classification. So basically, it's just an update of a classification node. Multi-label classification means that imagine that we didn't have to train two different models for L1 label and L2 label. Instead, we could get two labels at a time, and it will be these results will be provided by one model. And of course, we are looking forward to expanding the use cases of BERT. So, like question answering, similarity search of the text, abstract-based sentiment analysis, named entity recognition, and so on. And also, we are working on the blog post that is dedicated to this extension, and we are going to include some more details. So please keep in touch and read this blog post once it's published. And finally, I would like to thank my colleagues for their enormous contribution to this project. So Najat Buyataga, she is a PhD in NLP, and she helped us a lot with user experience of the nodes, preparing the use cases, finding bugs. And Alexander Bandaletov, he's a Java developer, and actually he made it possible, and he implemented these wonderful nodes. So thank you, colleagues. Yeah, and that's everything I had for today. Thank you for joining. In case you have any questions regarding BERT or any other extensions, or maybe you might be interested in our services that we provide, please feel free to contact us. And of course, now we are going to have a Q&A session, and I would be glad to answer your questions. Okay, let's see. Okay. Sorry, I need some time to read the questions and pick some. So the question is, L lower means faster. I'm not sure if you were asking about the lowercase, like uncased and cased models. No, I wouldn't say that it will run faster uncased and cased and versus uncased. If you're asking about the L as a parameter for one of the blocks in neural network, so yes. The less blocks you have, usually it works faster and it doesn't take a lot of memory or video memory. But at the same time, the results might suffer. So this is kind of a trade-off. If you take a lightweight model, it will run faster, it will train faster, but it might not give you the best results, and vice versa. If you take the huge model, it might provide you with better results, but it will the training process will take much more time. So another question. Yeah, so I tried to use BERT model selector, but I get the error message, could not start Python kernel. Error during Python installation tests, library is missing. Yes. So unfortunately, it's not the smoothest process for installation deep learning extension in KNIME, but they have a special tab in the settings that is called deep learning. So in case you have installed any deep learning extension, let's say TensorFlow 2, you should have this tab. So my recommendation is to go to this tab and create a deep learning environment from scratch. Afterwards, you would need to install additional packages for Python, and actually I mentioned them. So here you can find them. So if you take this workflow, you can find them in the description of the workflow, or you can also find them in the workflow hub. So yes, you need to do some preparation. So you need to install some specific extensions. So can you describe in a bit more detail what the AMS grad variant checkbox is for? So this is this is kind of a slightly different, just slightly different implementation of Atom optimizer. I cannot say for sure, but I just read an article a couple of days ago. It seems that those people who have implemented AMS grad, they found some kind of error in Atom implementation, but it seems to be not really significant error, and it just defines one of the Atom parameters. So basically, you can consider AMS grad as another option of optimizer. So unfortunately, I'm not that fluent with this math, so I cannot say more. But just please treat it as another classifier, or otherwise, I guess you need to read one of the papers describing this algorithm. So yeah, there is another question. Yes, slides and the video will be available after the webinar, so you can use this. I don't see any other questions. I don't know. Do I have to update it? Well, anyway, please feel free to ask questions. I will stay here for around 10-15 minutes, so we may have some kind of discussion.
Artem, thank you very much for that presentation. Again, does anyone else have any additional questions? Please put them in the Q&A. And I do see a couple of more questions coming in. If you want, Artem, if you wanted to address and maybe answer some of those questions.
Yes, yeah, I also noticed this. Okay, so one of the questions, do you know any practical use cases where BERT classification is used? Well, I would say the most straightforward is sentiment analysis. This is a binary classification. So in case you have like reviews from your customers, you can see whether they are satisfied or not. Or if you do some kind of sociological research and maybe you're using Facebook or Twitter or any other posts, you can take it. Another thing is that, let's say you need to categorize the documents in your organization, and in order to classify them by, let's say, finances or insurance or medical records, this is another use case. Yeah. So, so in your testing, what kind of performance increase did you see in CPU versus GPU with the nodes? I would say I have never trained the models on CPU because it just, you know, it takes eternity. I remember a couple of years ago, about 2 years ago, I started training the BERT model, but for quite different task, for another task. And there was something like expected time 48 hours. When I switched to GPU, it took 2 hours to train the model. So it's just, I don't know, maybe 10, I don't know, 100 times faster or something like this. So, you know, deep learning world is, you know, is using GPU always. So CPU is not applicable. Maybe you can try to train some models very shallow, very simple with CPU. But if you are trying to use you know, such huge models as BERT, or if you're building the models that work with image recognition, like using convolutional networks, you should always use CPU, GPU. Sorry. So that's the real world. Okay, so I guess that there is no more questions so far, but please feel free. Yeah, and regarding CPU and GPU, so probably you can do it this way. So training should always be executed on GPU, but probably you can try to deploy or apply your model based on CPU, because CPU fit in the model or applying the model that has already been trained is a less expensive operation, and this can be running on CPU. Yeah, this is the use case you can try on, but usually everything is running on GPU.
Well, Artem, I'm going to say a last call for any last questions before we conclude our workshop for today. So please, if anyone else has any last minute questions, if not, we will follow up later. Any questions? I think everyone has answered, you've answered all of everyone's questions. And so again, we thank you for participating in this workshop today and presenting for us.
Yeah, thank you for joining. Goodbye.
All right, goodbye, everybody.